Assalamualaikum warahmatullahi wabarakatuh. My name is HADI bin MUSTAKIM and my group consists of Tomili CHUIN, PUTRA SYAH and JIVETHA MURUGAPOOPATHI. And now I will explain a bit about the introduction. What is AFT of an image? The fast Fourier transform is commonly used to transform an image between the spatial and frequency domain. Unlike the other domains, such as RAW and radon, the FFT method preserves all original data, plus FFT fully transform image into the frequency domain, unlike time frequency or wavelet transforms. How to display FFT in MATLAB? Y equal to FFT, X computes the discrete Fourier transform, which is DFT, of X using a fast Fourier transform algorithm. If X is a vector, then FFT returns the Fourier transform of the vector. If X is a matrix, then FFT treats the column of X as vectors and returns the Fourier transform of each column. What is Fourier transformation in MATLAB? The Fourier transform in a mathematical formula that relates a signal sample in time or space to the same signal sample in frequency. The FFT function in MATLAB uses a fast Fourier transform algorithm to compute the Fourier transform of data. Okay, for the first task, I've been asked to visualize my original image into frequency domain using fast Fourier transform. Okay, this is the coding. First, I create a figure, then recall the address of the image, then I make a subplot. Then this is for the original image, and then for the gray image, I use imdata equal to RGB to gray. Then to get Fourier transform of any image, use f equal to FFT2 in bracket imdata. And Fourier transform of any image, s equal to ABS in bracket f. This is for the Fourier transform of an image. Okay, and then for the centered Fourier transform of image, use FSH equal to FFT shift in bracket f. Then for the log transform image, we use S2 equal to log 1 plus ABS in bracket FSH. And lastly, for the reconstructed image, we use F equal to IFFT shift in bracket FSH, F equal to IFFT2 in bracket F. Then I will run. So this is the result: the original image, gray image, Fourier transform of image, centered Fourier transform of image, log transform image, reconstructed image. Okay, that's all.
Greetings and good day to sir. My name is Tommy Lee and I will be presenting on task 2, which is to apply Gaussian smoothing filters on to images. Okay, so in this task, we have to apply a blur effect on our original image using the Gaussian kernel by changing the standard deviation value. So we have to compare at least 4 output images with different standard deviation. So, as a note to be taken, before we proceed, we must have MATLAB's image processing toolbox function installed before we can proceed on this task. Okay. On line 3, I'll declare the image, okay, I equal to imRead. So this is for us to call out upon the directory of our source image. Okay, so for the first half of our output panel, okay, we will filter the image with isotropic Gaussian smoothing kernels of increasing standard deviation. So I've declared here 3 output images to be shown later on the output, which is iBlur1 is equal to IMG Gauss field I2, iBlur2 is I8, and iBlur3 is I20. So later on the output panel, I have plotted the subplot to show the original image, and then the first blurred image, which is sigma equals to 2, the second blurred image, which is sigma 8, and the third blurred image, which is sigma equals to 20. So for the bottom half of our output panel, I'll be showing the filter image with anisotropic Gaussian smoothing kernels, as this allows Gaussian kernel to have different standard deviation along row and column dimensions. Okay, so here I've declared 4. So there's a iBlur x1, I in the array 8, 1, iBlur x2, I in the array 21, iBlur y1, I in array 1, 8, and iBlur y2, I in array 1, 20. So I've plotted the subplot to show the images with iBlur1 sigma x equals to 8, sigma y 1, for iBlur x2 sigma x 20, and sigma y 1. For iBlur y1, we have sigma x equals to 1, sigma y equals to 8. So as for the last one, we have iBlur y2, we have sigma equals to 1, and sigma y equals to 20. And now I will run the coding. Okay, so here we can see that in the top half, this is the original image. As we increase the standard deviation from 2 to 20, the output of the smooth image will be getting blurred, and it gets blurrier to the end. So the image will become less sharp. So this is for isotropic Gaussian kernel. As for the bottom half here, we have image where sigma x-axis equals to 8 and sigma y-axis equals to 1. As you can see, the image when sigma x 8, you can see the Gaussian blur effect is being shown here compared to sigma x 20, which is more obvious through the x-axis. So as for sigma y8, as you can see, Gaussian blur effect is being applied on the y-axis. With sigma y20, it gets more obvious with the Gaussian kernel. So that's all. We go on to task 3.
Assalamualaikum warahmatullahi wabarakatuh. So I'm Putra AZLAN Shah. So I will be explaining about task 3. So first let me share the screen. Alright, so for task 3, we are asked to detect the ages of your original image using Laplacian of Gaussian, which is log channel, and observe the changes in the output image as you change the standard deviation value. Compare at least 4 output images with different standard deviation. So, as we can see here, this is the coding for task 3. First, I have to predefine the log filter using fSpatial. This is using the standard deviation of first using 0.4. So if I use the standard deviation of 0.4, so the image will be like this one. So I can compare to at least 4 different type of standard deviation. So the standard deviation is this one. So if I change it to, for example, 1, and like this, so the image is like this. Next, if I change it to 0.05 at least, so the image will be like this. And the last one, if I change the standard deviation to, let's say, 10, so the image will be completely dark. So we can observe the changes in the image using the standard deviation. So the higher the standard deviation, the darker the image will be. So in conclusion, we have learned about fast Fourier transform, FT. Fast Fourier transform is a highly optimized implementation of the discrete Fourier transform, which is DFT, which convert discrete signals from the time domain to the frequency domain. FFT computations provide information about the frequency content, phase, and other properties of the signal. Besides that, we have learned about the signal processing. FFT forms the basic of frequency domain analysis, which is spectral analysis, and its use for signal filtering, spectral estimation, data compression, and other applications. Variations of the FFT, such as the short-time Fourier transform, also allow for simultaneous analysis in time and frequency domain. The discrete Fourier transform, or DFT, is the primary tool of digital signal processing. The foundation of the product is the fast Fourier transform, which is FFT, a method for computing the DFT with reduced execution time. Many of the toolbox functions, which is including Z-domain frequency response, spectrum and substrum analysis, and some filter design and implementation functions incorporate the FFT. So that's all from our group. Thank you.